Good morning, everyone. I hope you're having a great time in Vancouver. I've been to NeRFs in Vancouver in December, but I've never been in the summer, and I imagine it's lovely, and I hope you're having a great time. And I'm joining you here from home in San Francisco. And thank you for the intro, Genu. And I'm excited to talk with everybody today about a couple topics I wanted to do. So NeRFing and embodying language models. So there's really going to be two overall parts for the talk today. The first part is two different ideas in Nerf for robotics. And the second part is going to be the 3D story of Palmi. I won't have too many specific slides specifically on 3D, but I want to try to really help highlight the 3D parts of that story, because we did do some 3D neural scene representation fusing into language models in Palmi, and it's, I think, pretty interesting to compare with the other options we looked at as well. But first, though, let's do these couple ideas in Nerf for robotics. So, Jen, you mentioned in your intro for the overall workshop, certainly one of the main areas of research in the past couple of years in 3D broadly that a lot of people have been excited about is Nerf. And of course, there's many related methods to Nerf. I think Nerf itself is specifically large enough of a innovation, shall we say, that we can kind of just use a Nerf as a catch-all phrase for all the other related methods. And of course, they continue to develop. Specifically in robotics, I think there's been a handful of interesting ideas of how we can use Nerf in robotics. I think this continues to develop. I think Nerf is certainly very powerful, and there's much more to extract from existing Nerf methods and extend them more, potentially with feedback from sort of roboticists trying to use them in how we can make them better and better. This is not comprehensive at all, but I think here's a list of good list of a handful of key works in using Nerf in robotics. And one thing I want to think through with you is, I would say, arguably, for each of these four, which were some of the first ones in using Nerf for robotics, and this also would apply to a lot of other works trying to think about how do we benefit from the greatness of Nerf in robotics. I would argue that all of these four use Nerf to then bottleneck the entire method through some other 3D geometric representation, and then use that for the robot. And there's a lot of benefits of these methods, and they make a lot of sense. I do think that there are potentially other ways to use Nerf too. And we'll talk about that in a moment, but just to go through what are the different 3D geometric representations that are used in these different methods. In iNerf, the whole point is to estimate 6 DOF poses. In this DexNerf paper, they condense everything down to a depth image and then do grasping from there. In this navigation paper, everything goes through an occupancy field. That's kind of a first-class part of Nerf, but it is also somewhat separate of an idea from the actual Nerf itself. And then in this Nerf supervision paper, we go through key points descriptors. So these are all other 3D geometric representations that we are taking Nerf and bottlenecking through for the overall method. Instead, I don't think it is something that is uniquely necessary, but I think it's an interesting alternative to consider. The couple options that we're going to look at today instead send Nerf into the sort of overall robot policy without going through some other 3D geometric representation. I think that's kind of interesting. So let's go through these first couple for today. So this first one is a collaboration with Chelsea Finn and her students at Stanford. So Alan and Mujin, and then as well as Leray at MIT. And this paper is at CVPR this year. And I want to call out that the poster is on Thursday, and Alan is there, Chelsea's there as well for the next couple of days. And you should go talk to Alan on Thursday. I'll give you the sort of prep of the story, though. So one thing that I want to do before we get too much into the actual method is just take a look at sort of what does this, what generally we're talking about here in terms of what this enables on the robot. So shown here are some videos of rollouts of the resultant policy of training with this method, and a couple really nice things to highlight, I think. First is that this is a grasping method, which is closed loop and real time. A lot of grasping work is instead not closed loop, but instead just looks at the scene and then chooses a pose and then moves to it open loop. This is instead closed loop. You know this is closed loop because we can move around the objects in the scene and the robot will respond and go and grasp things. The other thing that's really nice, and it's really hard to achieve these two different things in conjunction with each other, is that the method works considerably well for even very thin and very shiny objects. And that is really challenging for a lot of more traditional, shall we say, 3D methods, and especially for grasping. So I think those are two pretty compelling aspects to have together. And I want to talk about how this works. In order to appreciate the sort of whole setup here of this method, I think it's useful to go, sort of away from vision and back over into robotics for a moment and think about learning from demonstrations. So very common setup in robot policy learning from demonstrations. One very concrete example might be we teleoperate the robot and we have a bunch of expert demonstration trajectories and we learn some policy purely with supervised learning. So this would be behavior cloning. And that's a very concrete example. A key, also Jenyu, I see you're moving things around. Is everything good?
It's good. It's just someone trying to record the meeting.
I see. Okay, no problem. So the a very fundamental problem that is very well known, talked about a lot in imitation learning, especially doing supervised imitation learning, is the problem of compounding errors. Just so we're all on the same page of what the problem of compounding errors is. It's I think helpful to visualize. If we have some kind of expert trajectory of states that we would hope that a learned policy would follow, if instead our learner is not perfect at matching all of the desired actions that an expert policy would follow, instead what we get is a little bit of error on the first action that the learner uses, and then that little bit of error might cause even more error in the second action that the expert would use, and this can compound, and the sort of error from nominal trajectories grows over time. There's actually a lot of theory on sort of bounds of what this error can be. It can be very bad, especially over long horizons, and this is a key problem in imitation learning, again, perhaps probably initially popularized by this dagger method cited here on the bottom from Stefan Ross. And we're going to talk about that method that they came up with in that paper. So there's been a lot of proposed solutions to compounding errors in the literature. We'll go through a few. One of them is the algorithm, well-known algorithm called Dagger, which was proposed in that paper that, again, I think is probably the one that popularized this whole concept of thinking about compounding errors. And the way that Dagger works, I think it's quite simple, the sort of key idea in it, which is all we do is we just ask the expert what they would do in the states that the learned policy ends up at that we don't want the learned policy to be in. So we ask the expert what they would do, and the expert will show the learned policy how to correct these things. Now, this all sounds good and dandy, but what this means is that we have to take our original data set, and we don't only have our original data set anymore. We also need to add another data set where we have an expert labeling the on-learner policy data. And in some cases, like maybe playing video games or other things, this is very doable. But in general, especially for complex context-rich tasks like visuomotor manipulation, I think this is highly challenging. So it's both a nice idea, but it's also certainly not the end-all solution for compounding errors. Another idea, which is nice and very simple and has some nice both theoretical and practical properties, is this idea called DART. And the idea of DART is during the expert demonstration process, we actually go and inject noise into the teleoperator's actions that are applied to the robot. This is a concrete example of doing that. So what this means is the actual demonstration, the original expert data set is no longer the same. We don't have the same original expert data set that we had before. We instead have a noise-induced expert data set. What's nice is we only need to collect that one data set, and we don't need to do any of this funny business of having an expert label what the on-learner policy should do. But we have kind of, in some ways, affected the quality of our original data set. And this can be not necessarily advantageous. It's also hard to know what is the scale of noise you want to add. this is potentially kind of tricky. So just to visualize kind of in this trajectory view, what happens here with this Dart noise injection process, we force the original data set to make it so the expert has to show how to recover from mistakes. And with the data set now having many examples of how to recover from mistakes, the learner can learn how to avoid compounding errors. So that's Dart. Dagger and Dart, these are two common methods. A third method, which doesn't really have any formal name, and the first time I actually know of somebody doing this was we included it as kind of a side note in a paper, which was actually the last paper that I did in grad school. It wasn't the key point of that paper. It's an incredibly simple idea. It's like super obvious, so we didn't try to claim it as a major contribution, but I think it's actually pretty useful. We can call it noise augmentation. Kei Ke had another paper where I think she independently came up with the idea, and the focus of her paper is on this concept, and she has a very nice analysis of it. I cited her paper at the bottom as well. So I think we can call it noise augmentation. And let me show you what it does. But before, I just want to call out that an excellent part of using this method is that we don't need any data and we don't affect the original expert trajectories. So we still have the original expert trajectories. There's no quality degradation there, and we don't need to collect any new data. So it's very nice and simple in that way. It's kind of the key advantage of it. So the idea behind this noise augmentation is to take that expert trajectory and don't collect any new data, but just through pure augmentation, imagine that we had messed up trajectories and also imagine how to correct them. And there's various details of how to do this. But we can kind of concretely walk through this as saying, okay, we have some state ST, and we're going to add noise epsilon to it. And then we're going to compute what the corrective action would be. In the general case, you can do this with kind of some noise distribution and a perfect inverse dynamics model. So let's add that to our little visualization here. So if we have some noisy version of state 2, then we can compute how to correct back to the nominal trajectory that we want to be on. Or we have some other noisy state, and we do this for all the different states in our data set. Okay, that's great. And what that means is when the learner is rolling out its learned policy, when it messes up, these messed up states that it ends up in are sort of in the region of attraction of the augmented states in our augmented data set. And so purely through this way, we can actually teach the method to recover from mistakes just through augmentation. In terms of the noise scale, even just a very small amount of noise can significantly help here. This is a table I just pulled from my paper from a while ago, where the details don't matter too much here. The point is just that the numbers difference in this case was massive. Like basically, this trick alone took the method from not working at all, 3 to 5% success, to 95% success range in certain cases. So it can be really massive. And I remember the noise scale here was just, standard deviation on the scale of 1 millimeter. So very, very tiny. This is not imagining huge errors, just very small errors that can avoid compounding over time. The major limitation, though, with all these prior uses of this method is that we only ever applied it to state observations. Both in my paper and in Kay's paper, is only ever applied to state observations, so nothing visual. And that really kind of has prevented it before from being something that is more a generically useful method. Instead, Dart and Dagger, you can use those with visual observations, no problem. But this has been a key limiting factor. And that is something that we look at resolving in this Nerf in the palm of your hand work. So imagining new visual observations, that seems like that's a pretty good fit for Nerf, and that is exactly what we do. So the idea behind using corrective noise for offline vision-based imitation, which is what we do here, with a bit of a focus on closed-loop 6-stop grasping tasks. If we think about, here's just a concrete scene. How can the robot grasp the wine glass? We've got a wrist-mounted camera here. The key insight is that the changes in state, if we have a wrist-mounted camera, equate to just different camera views. And that's a really good fit for novel viewpoint generation methods like Nerf. Note that it does mean that since most novel view synthesis methods especially work best if the scene is static, we're going to stay in static scenes during training. But what we're just going to do is we're going to imagine different perturbed wrist camera observations, and we're going to compute, since we have all the states of the trajectory, we know how to compute the corrective actions to get back to our nominal trajectory. and we're going to apply this feedback augmentation method. We call this Spartan. It has a nice little acronym, synthetic perturbations for augmenting robot trajectories via Nerf. Just to give an example of how large the scale of these synthetic views look like, here's what some of them look like both in simulation and in real. As you might know, Nerf is especially good at doing kind of mostly interpolation, shall we say, view synthesis rather than extrapolation. And that is a great fit for this application because we only really want to do views that are very close to our original training set, just maybe slight modifications of it. So it's really in a good regime for Nerf to be working well. And then I'm about to show you a bunch of simulation experiment results, and I just want to give you a visualization of what these simulation experiments kind of look like. So this is a simulated environment from one of Leroy's prior papers. So we look at the results. I think the quantitative results really tell a pretty compelling story, I think, which is if we look at a few different comparisons here, all in this not too big, but very information-rich table. The first is that just doing these synthetic perturbations, we can get an RGB-only grasping policy. And this, by the way, is on complete withheld test set objects. So there's this is generalizing quite well. So this is on grasping objects that are not in the training set, a complete, entire, actually different data set, not just a test set of that data set, but a completely different data set that it was trained on. We see a pretty substantial increase in the RGB only grasping on these objects. So increasing from 29% to 75%. That's a pretty sizable increase there. The only difference between those methods is just using these synthetic perturbations with Nerf. Another point is that we can outperform the sort of Dart style online noise injection when we have the same number of expert demonstrations. And the reason there is because we can just increase purely through feedback augmentations as many imagined trajectories as we want. If we instead limit the amount of different imagined views, then Dart and Spartan you would expect to be similar, but that's not really kind of the important comparison. It's a useful comparison to think about, but the one we're showing here is where we have the same amount of expert demos. And Spartan, we can arbitrarily make that as many augmented demos as we want. So that's, again, I think quite an advantage. It also can even start to outperform methods that use depth cameras, including the Dart version of those. So this is showing where Nerf is there. This style of using this augmentation together with Nerf is starting to outperform grasping methods. Typically, grasping methods, especially in simulation, work very well with more raw 3D representations. They just generalize super nicely, but we can start to outperform those as well. And it even starts to do quite well compared to methods that use additional online data. So doing like online reinforcement learning methods, which would need to collect millions of additional environment interactions. So quantitatively, the results are really quite nice. And I think this is a pretty rigorous set of evaluations that we're done here. In the real world too, it can work quite well. So this is even just grasping from a pretty small number of demonstrations. Here, the robot is grasping a banana with 14 demos. Here's the vanilla BC method on the left, Spartan on the right. This is actually a pretty tricky object to grasp because you can only grasp it from a very select set of orientations because it's too wide for the gripper, and on the other orientations, this thin box. You can see the vanilla BC method when it does fail. It looks like these very typical failures that we get with compounding errors where it just kind of ends up in a funky spot and it doesn't know how to recover. Whereas on average, Spartan method is much better at sort of recovering from these. Here's another one on the top. This is a very thin and very shiny object. This fork, again, can get pretty nice grasping results. And the wine glass is both very thin and very transparent. Again, very challenging for a lot of different types of traditional methods. Quantitatively, in the real world, overall a nice boost from using Spartan for the real world results as well. And again, this combination of closed loop and real time together with thin and shiny objects, I think is a pretty nice combo. So that was Spartan. A couple things I want to note is, as we were talking about before, instead of going through some intermediate 3D representation, here we are using Nerf to offline synthesize a robust RGB only policy. So all the Nerf goodness gets encoded into the weights of the policy, and there's no Nerf training or inference required at robot policy inference time, which, as you know, sometimes these methods can be computationally intensive. So it's nice that there's nothing required, anything at all in that regime at policy inference time. And then in terms of limitations, I think good to point out, one primary area, would love for people to think about extending it, would be to get this to work in more fully dynamic scenes. Again, we sort of made the assumption that at training time, the scenes are going to be pretty static. The policy can then generalize to a little bit of motion, but it's not really intended to work with very dynamic scenes. A definite area for future work. So the next NeRF in robotics paper I want to talk about is this reinforcement learning with neural radiance field paper. This was a collaboration with Mark Toussaint's lab at TU Berlin, led by Danny Dreiss. You'll hear more about Danny with the next paper I'm going to talk about as well. And then we also had Yunju from MIT working with us as well on this one. So RL with NeRF. So a couple key ideas here to think through. One is, it might be a pretty nice idea for robots to model the world with NeRF. And that sounds good, but it's not clear exactly what we want to do if we model the world with NeRF. We can synthesize views, but then it's kind of tricky to think about different ways to then just directly use that for having the robot use that for a policy. Another idea that we are going to build on is modeling the world as a latent condition NeRF. And this was, as far as I know, first done in the NeRF in the Wild paper. Here, the things that change about the scene in this visualization on the right are more of like weather and lighting effects, things of that nature. But we're actually going to use this to model other very important types of changes too, which we'll see, which includes actually, for example, objects moving around or objects being present or not being present. And that is the key idea of NeRF RL, is to use the latent code of a latent condition NeRF as the scene representation for policies. We use this for reinforcement learning, but you could use this for any type of policy learning that you'd like. And this really is the key idea. And I think this is a actually super general idea. It seems to work very nice in these experiments from this initial paper. And it would be one that I would definitely be curious to bet on more as we do more in this area. So in addition to latent condition NeRFs, which again, as I mentioned, is from the NeRF in the Wild paper, another key idea that I just want to acknowledge, Pixel NeRF, there's a couple others that came up with this, is not just having a latent condition NeRF, but have a latent condition NeRF that is conditioned on, shall we say, current images. So image conditioned latent NeRFs. And this is a key idea, which then allows us to adapt the latent condition NeRF to observations that we're seeing now, so to speak. This is going to be very enabling for us as well. So the overall key process of NeRF RL is all, I would say, visualized in this one key figure. So there's two overall steps. The first is that fully offline, we're going to train an encoder decoder where the decoder is a NeRF and the code is the latent space that we're later going to use for the policy. But this first phase, we have multiple different views. We're going to have, if we want, we don't need them though, we can have masks for these different multi-view observations, so masks of different objects in the scene. Again, we don't need them though, but they can be nice. We can use those if we want. And we're going to train this. We're then going to freeze everything. We're going to freeze the encoder and the decoder. We're actually going to throw the NeRF decoder away, and we're only going to use this encoder. And we're then going to train RL policies on this frozen encoder. So this is the overall process. What does some of this look like? How do we train this thing? These are some simple simulation experiments, but this is a gist of kind of the variations in these ones. So this is this sort of three-dimensional mug hanging, shall we call it, experiments where we have a mug. The mug is actually varying in a few different parameterizations of its geometry. And then there's also this hook that it's supposed to get onto that is also varying in different aspects of the geometry. We send a bunch of different input views sampled all over the space to train the encoder decoder of the NeRF. And then we would later train RL policies on this. So this is using PPO to do reinforcement learning, and it has a dense reward telling it to how to get the mug on the hook. And this is an example of both the resulting RL policy, which learns to put the mug on the hook, which is what we would hope. Great, RL works. And then also on the right, this is showing what the NeRF reconstructions look like. So very nice. This is again a very simple synthetic environment, but very nice, dense reconstructions in terms of novel view synthesis of these environments. Here's another one. This one is also, I would say, another pretty simple environment, but it has a couple key aspects of challenge. So one is that in this one, we have either a blue or a yellow block. So we can have objects either be present in the scene or not, and that will all work fine in this framework as well. And in this one, the policy is going to learn to, if it's a yellow block, push it to the yellow side, and if it's a blue block, push it to the blue side. So there's actually, it seems simple to a lot of people, but some type of very single point of contact pushing task is actually pretty tricky for policies to learn. You need a lot of feedback. This is something that RL can do quite well. Great RL works, but it's nice as well. You can see on the right, we get these really nice reconstructions, and the RL policies can train very well on this frozen NeRF trained encoder. More specifically, though, just that it works, is it actually seems to work very well. So in the experiments, we found that these NeRF RL style of training can actually outperform things, including like the ground truth states of these objects, where the ground truth states, since there's variation of different shapes, they're sort of expert knowledge chosen key points, also works better than a couple of other different types of autoencoder or contrastive learning baselines. So that's kind of the key takeaway. This seems to work very well in these experiments as being a representation for reinforcement learning. So again, I think it's interesting to note, this uses NeRF offline to guide an image encoder to produce a good latent space. And these are the same 2 points as with our last method. The NeRF goodness gets encoded into the weights of the policy, and there's no NeRF training or inference required at all at robot policy inference time. I think these are both really nice properties. Another sort of just like looking back at this method aspect is this is very similar to a super classic style, or maybe classic's not the right word, but been around the block style of doing policy learning, which is we train an autoencoder and then we just use the encoder for policy learning. This has been done many times. Here's a couple of key references. But the key difference with this is that the decoder is a latent condition NeRF. So some limitations. A primary one is that, I would say these experiments that we showed were still very much in the kind of simple simulation environment regime. And in practice, it might need a fair bit of work to get this to work sort of in the real world, especially, shall we say, in the wild. I think in the real world, in kind of more constrained scenes, this could actually work quite well. Danny has some results in a related paper doing more dynamics rather than RL, that it can work quite well. But in the wild, it might be pretty tricky. So I think that's a great area for thinking about for future work. Okay, looking at time, I have one more thing I want to run through, which is Palmi. So Palmi is an embodied multimodal language model. This is work with a bunch of colleagues from Google listed here. And there's a lot of different aspects of Palmi. We have been very excited about this work. On the one hand, Palmi is one model that does embodied robotics tasks, vision language tasks across multiple robot embodiments and across multiple modalities, including 3D neural scene representations, which I'll show you. A key aspect of the experiments that we saw with Palmi that we are excited about as well is that we get significant positive transfer from other domains, so vision and language, into the embodied domain. Palmi turns out to be a pretty competent visual language generalist and gets state-of-the-art on the OKVQA dataset for our largest 562 billion parameter model. We also saw some interesting aspects of minimizing catastrophic forgetting with scale, and we get some emergent visual language capabilities like zero-shot multimodal chain of thought. This is kind of the overview of what Palmi is and some different things it can do. Where in the middle, here we have kind of a simple architecture visualization of the key idea, shall we say, of Palmi is having text be encoded together with other modalities into a language model, which we all train together. And then we use this for embodied tasks as well as general visual language and language only tasks. Here's a couple examples of the multimodal chain of thought capabilities that we are able to see with Palmi, which, as far as I know, is the first zero-shot multimodal chain of thought capabilities to just sort of emerge from a large language model that had been adapted to be multimodal. So on the top left, this is a picture of Kobe. The prompt is, given this image, question how many championship rings did the player on the left win in his career? Answer, we can prompt it to say, let's think step by step. We never trained it with any of these types of traces, and the model can just respond by saying, Kobe Bryant is on the left. Kobe Bryant has won 5 championship rings. On the bottom right, this is another, I think, very compelling example. We actually did not train the large Palmi model at all on any multi-image examples, but we can get zero-shot generalization to multi-image comparative reasoning. So in the bottom right, this one is photo 1, insert the first image, photo 2, insert the second image, question what is in photo 1 but not in photo 2, answer let's think step by step and explain, and the model can just respond. Again, it's never been trained ever on multiple image examples, and it can say photo 1 has sunglasses on top of folded clothes, photo 2 does not have sunglasses on top of folded clothes, therefore sunglasses are in photo 1 but not in photo 2. Some other examples here as well. For real robot results, in terms of time, I want to get going, so I'm actually going to skip them, but there's a bunch of nice ones at our website. I think it's the best place to see them. Maybe if we have more time at the end, I'll come back. To cover some related work, just mention some things briefly. There's been a lot of work, and actually, Jen, you mentioned some of this in your intro, in using LLMs for robots for high-level planning. A key difference, at least with work from our own team, and in contrast to a lot of other works that have been done in the field, with Palmi, we actually have a multimodal LLM as opposed to a text-only LLM that we somehow graphed other representations into text. With Palmi, we directly train a multimodal large language model. And this work is very much enabled by the advancement of making language conditioned policies work better and better. So Palmi does not directly output actions to run on the robot, but rather outputs short horizon language instructions that lower level policies would then run. There's a ton of other related work generally. Also, I want to just briefly mention as well in multimodal language modeling. One particular one I want to highlight and give some attention to is this Frozen paper. It didn't necessarily have fantastic quantitative results, nothing state of the art, but it was a really interesting study and one of the first looking at just directly graphing vision encodings into language models. A lot of interesting results there, as well as there's a bunch of other multimodal language models that have come out over the past year. Flamingo, another very pioneering one. Poly, another Google model, state of the art on many tasks. Blip2 is a really nice model from Salesforce. Cosmos One, Microsoft, GPT-4, OpenAI, of course. These are all in this category of vision and text models to text. Another very relevant and inspiring work here as well I want to acknowledge is the Gato work from our colleagues from Deepmind as well. Okay, so a couple key questions with Palmi that we looked at in this paper. So one, very precisely, is can multimodal features be input to an LLM while leveraging the generalization of LLMs for embodied reasoning and planning? The second one is looking into different types of multimodal input representations, which I can show you more about. And the last one is just sort of other key aspects of training these models. Can the LLM be frozen or fine-tuned? What type of pre-training is best for the encoder? Sample complexity, things like this. One more actually set of research questions as well is around large scale. So scaling the model, scaling the language model, scaling the VIT, scaling the tasks, and things that sort of emerge from that. So minimizing catastrophic forgetting and other capabilities like zero-shot multimodal chain of thought. So a concrete way, I think, to think about, what are we sort of after here with some of the things that we do with Palmi, specifically in the embodied domain, is we want to take some language model and have some input long horizon, big picture goal, like how to move the yellow block on top of the blue plate. And then we want the model to come up with a potentially very complex plan that is required in order to achieve that goal. So like this example, output text on the right. But we want to ground the language model directly on observations of the world. So we want to be able to input the current views of the world into the large language model. You might think about how would we do this? What a lot of prior works have done is looked at describing the world in text and just putting into the language model. And this might work okay for some scenes, for some types of applications you might think about, but in general, this is pretty tricky to do. Think about trying to describe exactly such that you could sort of paint this picture, for example, and this isn't even a necessarily super complex a robotic scene, but it's one that's sufficiently complex to, okay, it's kind of hard to describe in text exactly how this is all put together. An image is worth 1,000 words. So we're going to look at learning an encoder directly from visual observations of the scene into the language model. And we look at a few different things here. So not just actually visual observations, but also using raw state observations, as well as pixels or pre-trained 3D neural scene representations. We also look at fine tuning or freezing the language model, a bunch of things like that. A visualization of how Palmi works, and to walk through a little bit of the details, if we have some text and we tokenize that into some text tokens. So concretely, these tokens might be something in RD, for Palm 8b. This is a 4096 dimensional vector. We have the sequence of all these 4096 dimensional embeddings, and we're going to throw that into Palm. And we're training a prefix large language model. So we have some sort of prefix like how to grasp the white object answer. And then we're going to train the model to complete these next tokens. So this might be what a long completion looks like for this example. But then when we do the grounding of observations into the language model, we can think about having some vision observations that go through some encoder. And we are going to map the encoder also directly to the same dimensional space as the text token. So we're going to use a sequence of these. We use 256 for each image. And these are going to be the same dimension as the text tokens. And we're simply going to inject them into the language model and train through the encoder and potentially through the language model in order to get this whole thing to predict these text tokens on the other side. So that's the gist of making Palmi a multimodal vision language model in one case. However, what we're going to do is we're going to interleave these images into the text. This is something as well done in papers like Frozen or Flamingo. So we're going to say, okay, given this image, now this image is interleaved within the text. This helps in these sort of downstream emergent properties like multi-image reasoning. Given this image, how to grasp this object, this is how we generally would form this prompt. A little bit of the 3D and actually object-centric things as well. This is something that we also studied in Palmi. It ends up not being the main story of Palmi, to be honest, because Palmi ends up being quite compelling at just sort of the general nothing fancy needed vision case. But one thing we looked at as well is using the large language model to have object-centric representation such that it can refer to entities. So what we can do is we literally say in the prompt, object one is, and then we insert the tokens of one specific object. In this case, we would assume that we have object masks. Then we can say object two is blank. What's nice here is that then the outputted text can refer to specific objects because it has been grounded on these specific objects through the formation of the prompt. And this can help, for example, if Palmi is trying to communicate with a lower level policy and it's hard to describe in text what it wants to do. Let's say there's a bunch of different objects that all look similar. It can be hard to describe in text how those different objects are distinct from each other, but we can just have these multimodal tokens that are grounded specifically on ones that it's trained to do. And this is where the 3D neural scene representations came into the Palmi experimentation, because we wanted to be able to train these object-centric representations fully autonomously without any type of object mask. And the way we're able to do this is with object scene representation transformer. This is a work from Mehdi on our team. And so similar actually to NeRFRL, what we do is we train the OSRT encoder decoder, then we throw away the decoder, and we insert these slots as these object-centric representations into Palmi. And that's how that works. So a couple minutes, I'm going to try and leave a couple minutes for questions. So with that in mind, I'm going to kind of do some skipping, but I do want to highlight one of the key results, especially with respect to the 3D part of Palmi, is that this OSRT style of pre-training, that's shown on the bottom here, can get very compelling results. This is even in a very low data regime where we only have about 100 examples for these different planning tasks. Very compelling generalization using these OSRT pre-training style. The sort of however, I would say, and it depends on what your preferences are, OSRT, that doesn't need any large-scale pre-training vision data. It gets quite good results through the structure of that model. But another very compelling option is to use a massive vision transformer trained on billions of examples and co-trained with all of your vision language data and all of your different robot data sets. So that's that VIT4B mixture, full mixture line. And that actually ends up getting pretty comparable results on not all, but many of these different tasks shown here. 74 to 76, that's not a huge difference. 74 to 82, that's a little bit larger of a difference. But this actually really, this large scale vision pre-training also really helps these results. And if the line just above it is VIT4B without all this vision pre-training, nowhere near as good results. So basically the point here is that either using some type of structure like OSRT or doing large-scale vision pre-training, both, if applicable, are very effective. The thing is, though, we can easily just apply this large-scale vision pre-training to any environment without needing any domain-specific data. That's kind of the challenge of the more OSRT style, is we need a ton of domain-specific data. So there's key trade-offs there, which we can talk about maybe at the end. I'm going to skip some of this, skip what the training mixture is. You can look up in the paper. We ran Palmi in a bunch of different robot environments. We got, I think, really compelling transfer results from different domains into the embodied domains, skipping some other things for time. Palmi is a really good visual language generalist, again, sort of state-of-the-art at OKVQA, also pretty good results on data sets like VQA v2 and COCO, although not quite as good as models like Poly. There's plenty more of these zero-shot multimodal examples on the website. The scale catastrophic forgetting thing is really interesting. And jumping to the end, Palmi is an embodied, an investigation into embodied reasoning as vision language modeling. We looked at a bunch of different types of transfer. Palmi is a competitive general visual language generalist. And we looked at other input representations besides just raw vision. And the sort of 3D question I would encourage people to think about, at least it's something I think about quite a bit, and I think is pretty compelling to wonder where this goes, is that large scale, massive scale, billions of images, 2D vision only pre-training is extremely powerful. And it's interesting to try to capture sort of the best of both worlds. So 3D, often it's not really a thing at the moment. It's at least not nearly as common as it is with just 2D images to do that level of scale pre-training. But I would suggest that that could be a quite compelling area for more people to be working in, which is truly large scale 3D generative modeling from images or other raw representations. So with that, I will close. And if we have any time for questions, I'm happy to take some questions.
Thank you, Fit. And do you have any questions? Through Zoom or like through the, if you have any question, you can come up to the microphone, directly ask.
Yeah, nice talk. About a question about really the representation. If you look at large language model, you don't explicitly represent concepts and like relationship, right? Do you think for robotics you actually do need like these object-centric representations, like have these slots and explicitly?
Yeah, it's a great question. I think that depends on your philosophy. I would say I'm open to different philosophies, but I think maybe the one that's hardest to argue with at the end of the day is just run some quantitative experiments of trying one version versus the other, and that's what we try to do. And I think actually, especially if you have massive enough pre-training, both on the language and vision side, you can do quite well without any type of object-centric representations. Arguably, you could say language itself is really nicely kind of a object-centric representation, so to speak, but it can be trained just from large-scale data. But the object-centric versions that I talked about as well can have advantages. Both can work. But yeah, I would not underestimate the value of, not designing anything specifically object-centric and just training from massive scale vision and language data. It is quite compelling. Yeah.
All right. I guess, yeah, we don't have time for more questions, but there are a few like questions over Zoom. Maybe Yeah, I guess maybe you can discuss this offline by sending emails to Pete. And again, thank you, Pete, for your great presentation. And thank you.
Thanks, Jenny, for the invite.